Hello and welcome to our lesson on factoring squares and cubes. Technically what we're going to be factoring are binomials that contain what we call a difference of squares or a sum or difference of cubes, so I sort of condensed that title there. To recall, factoring is a process of writing one polynomial as a product of two or more, and we can sort of think about it as the reverse of our multiplication process. So you can see where we're going here. Let me show you where some of the problems that we're going to be dealing with come from. So let's say we were to multiply out this set of binomials, the 4x plus 9 and 4x minus 9. These are special binomials called conjugates. Not sure if you know that word. But what's special about conjugates is when we multiply them out, let's see what happens. And actually I want to move this. Why I put this over here. When we multiply out conjugates, so starts similar to in our last topic. 4x times 4x is going to give us 16x squared. And then 4x times negative 9 gives us a negative 36x. And then 9 times 4x gives us a positive 36x. And then at the end here we get a minus 81. So this sort of starts the same way it did in the last topic, where we combined the like terms in the middle and we ended up with a quadratic trinomial that we were trying to factor. But here, what happens to the two terms in the middle when we cancel them out? Well, positive 36x and negative 36x cancel, and we're left with just these two terms, which we call a difference of squares. So remember, going in this direction, that's the multiplying process. That's not what we're trying to do here. We're not trying to take the product, multiply out, and end with one polynomial. We're trying to start with this one polynomial and figure out what to... Now I gotta move this again. We're trying to figure out what two polynomials we had to multiply to make that thing happen. So working from this binomial back to these two binomials is the factoring process we're going to look at here. Okay? So why did the two terms cancel? I suppose is the real question here in this problem. So when we multiply the conjugates, because these two binomials match, right? The first terms are the same, the last terms are the same. The only difference is a positive and a negative in between the terms. If that is going to be true, then the positive and negative of the same number will happen every single time. So those middle terms will always cancel, leaving us just these two terms. And because these binomials match, the 4x times the 4x, right? When we multiply something by itself, 4x times 4x, we call that squaring that thing, right? So 4x squared, both of those would produce that 16x squared. And then 9 times 9, multiplying it by itself gives us the 9 squared. So these two terms that are remaining, they're perfect squares. They are the result of squaring something. And then the minus in the middle has to occur because if we have a positive and a negative to make the middle terms cancel, that last product, positive negative, will have to be negative. Okay, so when we're working on factoring these differences of squares, the process is going to be pretty easy. We just got to figure out, well, what did we square here to get this first term, and what did we square here to get this last term, right? It's not so bad, and we'll get to some examples in a minute. The only problem I see people having with this particular type of factoring process is trying to apply it to something that is not a difference of squares. Okay, so let's first talk about some criteria. What does it mean for us to be factoring a difference of squares? So if a polynomial is a difference of squares, then it has two terms. So we won't use bottoms up, on a binomial. We use that for trinomials. This is two terms, and not just that, but they have to be subtracted. There's got to be a minus in the middle. It has to be a difference of those two terms. And then any coefficients or constants, like the 16 is a coefficient of x squared or the 81 is a constant. Any coefficients or constants, they have to be what we call perfect squares. They have to be the result of squaring a number. And these are really some squares that you should be familiar with, but just to dust off the cobwebs, I want to make sure that these numbers are on your radar. So obviously 1 squared is 1, 1 is a perfect square. 2 squared is 4, 4 is a perfect square. So is 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. Again, most of these you should be pretty familiar with. You should recognize them as perfect squares. After 12, maybe I lose a few of you, but 13 squared is 169. 14 squared is 196, and 15 squared is 225. So when you're looking for a difference of squares, you're looking for any of the coefficients or constants to likely be on this list, okay? And then there's a rule for the variables, in particular their exponents. Exponents on the variables, they have to be even. And that's because your difference of squares is always going to be the result of multiplying conjugates. So conjugates, again, means you have the same terms but opposite signs, like an x plus 9 and an x minus 9. So we have to have an even exponent as a result because the terms here have to match. So if I had 1x here and 1x here, that would give me 2 altogether. Or if I had 2 here and 2 here, that would give me 4 altogether. Or if I had 3 here and 3 here, that would give me 6 altogether. So if these match, anytime we add two numbers, we're going to be resulting in an even number. Okay, so we have to have an even number of exponents that are going to break into those two conjugates. Okay, I suppose I could have left this. All right, so how do we go about now factoring if we've established that what we have is in fact a difference of squares? Well, we know that our difference of squares is going to factor into conjugate binomials. Conjugate binomials. So I like to set up my parentheses, put a plus in one, put a minus in another, and then I'm going to rewrite my terms as squares. I just want to figure out what am I squaring to get to the terms that I'm left with. So looking back at this 16x squared minus 81. Okay, instead of multiplying, if I was starting with my 16x squared minus 81, what I want to know is what did I have to square to get this, and what did I have to square to get that? Well, basically we're taking the square root of these numbers, right? So the square root of 16 is 4, and 1x squared, right? So if I square 4x, 4x and 4x is going to give me that 16x squared. Or if I square root 81, I get 9, so 9 squared. So these two right now are equivalent, right? 16x squared minus 81 is the same thing as 4x squared minus 9. So I just want to figure out what I'm squaring to get each of these terms, and then those are going to be what goes into my conjugate binomials. I'm going to have a 4x plus the 9 and a 4x minus the 9 when it's all factored out. Okay, so we want to figure out what we're squaring to get each of our terms, and then you're going to set up your parentheses. Let's go and write that word out. Set up your parentheses. For the binomials, again, one with a positive, one with a negative, and it's the bases of the squares that go into each binomial. Again, the bases of the squares, so the 4x and the 9. Both start with a 4x, and then both end with a 9, which has got a plus and a minus. It's the only difference. Okay? And then remember, this is only a process that we can apply to a difference of squares. Difference of squares. Okay, so let's try this out. So obviously x squared is already a square. What are we squaring to get 16? Would be 4, right? So if we took the square root of 16, we would get 4. So if x squared minus 4 squared is going to factor into an x plus 4 and an x minus 4. So these bases of my squares, that's what I have in my conjugate binomials. So x plus 4, x minus 4. And then here, to get 9x squared, I'd have to be squaring a 3 and an x. And to get 1, I would be squaring a 1. So a 3x plus 1 and a 3x minus 1 when we factor. Pretty simple, right? Here, to get 36x squared, it's 6x squared. And then to get 49, we're taking 7 and squaring that. So we're looking at a 6x plus 7, 6x minus a 7 when we factor. Okay, and if you're not so comfortable with the squares, I mean, we have the cheat sheet here that we wrote, but if you can also use your calculator, you've got the square root button here, so if you took the square root of 49, then you'd be looking at 7 as that result. Okay, so feel free to use your calculator if you're not so comfortable with some of the math facts. All right, how about number 4? Let's see. X to the 4th, right? X to the 4th, what am I squaring to get x to the 4th? Well, that would mean an x squared would have to be in each binomial. And then the square root of 81 is going to give us 9. So I'm going to have an x squared plus 9 and an x squared minus 9. So x squared plus 9 and then x squared minus 9. Now, if we look carefully at number 4 here, we're not actually done. So when we're factoring, we want to make sure that we're factored completely. And what you should notice is that this second binomial contains another difference of squares, right? This is x squared minus 3 squared here. So we can continue. X squared plus 9, the sum of squares is not going to work the same way, and we'll talk more about that in a few minutes. But for now, let's leave this x squared plus 9 here. The x squared minus 9 can become another x plus 3 and x minus 3. And that would be our completely factored answer. So you want to make sure that you're factoring completely. And that's kind of a special one. You're not going to see that happen a lot, but make sure you're factored completely. Okay? Here, if I took a 3x and squared it, I'd get 9x squared. And then if I took 10y squared, then I would get back to that 100y to the 4th, right? The square root of 100 is 10, and if I took that y to the 4th and split that into 2, I'd have to have y squared in each of those binomials. So a 3x plus 10y squared and a 3x minus 10y squared. 3x plus 10y squared and 3x minus 10y squared. Okay, cruising right along, and then we see number 6. I don't know about you, but I encounter a lot of people that have some phobias with fractions. That problem looks pretty ugly. But the fractions aren't going to change anything here as long as our numerators and denominators are all perfect squares, which they are. So what are we squaring to get 1 is 1. What are we squaring to get 4 is 2. So the square root of 1 over 4 is going to be 1 over 2. And if I have 6 x's here, then 3 are going to go into each binomial. And then the square root of 16 is 4. The square root of 49 is 7. And I would have to have y squared in here to get to the 4 altogether. So 1/2 x cubed and 4/7 y squared are the bases there. So 1/2 x cubed plus 4/7 y squared and 1/2 x cubed minus 4/7 y squared. Ugly, but manageable. Okay. I've got one here for you to try. Something a little different going on in this one. Maybe you see it. If you feel confident, go ahead and pause. If not, remember when our first term is negative, we want to factor out that negative. So the first thing we should be doing here is taking the negative 1 out, which will make this a positive 144x squared and then a minus 1. So this is really a negative 1 times, this is going to be a 12x squared and 1 squared. So we're going to have a negative 1, a 12x plus 1, 12x minus 1. And then we're good. And remember, I'm not really doing this every time. You know, you should pretty much have some confidence in what you're doing, but if you wanted to check your work and you weren't sure that it was right, just do a quick multiply this back out. So let me just show you that here, right? This would be 144x squared. Oops. 144x squared. Here's a negative 12x and a positive 12x that will cancel. And then here's a negative 1. So these will cancel, and then when I redistribute the negative 1, I get a negative 144x squared and a positive 1, which is exactly what we started with. Okay? So if you want to do those checks in your head or do them on paper, either way you can always check your work with some multiplication or redistribution. Where am I? There we go. Okay. Now number 7, what's happening here is what I sort of mentioned here. Some of you may still be wondering why we could continue with the x squared minus 9 but not the x squared plus 9. Well, what's going on with a sum of squares versus a difference of squares? So I see people want to go, okay, well this is 5x being squared and this is 2 being squared, but if there's a plus there, now what? Well, maybe I'll just, and I hope you're not writing this, I'm sorry, I should have said that. If I just make these both positive, will that take care of my issue? Well, there's 25x squared and there's plus 4 at the end, but what we also have in this one is a 10x here and a 10x here, so we do get the 25x squared and we do get the plus 4, but we've got 20x in the middle, which is not what we have here. not what we have here. So that can't be it. So then I'll see people go, okay, well maybe I'll just make them both negative, right? So if I make this 5x minus 2, 5x minus 2, well, 25x squared, good. But now negative 10x and negative 10x makes negative 20x in the middle, and then plus 4. So again, not what we have here. So what's going on with this is that it's not going to be possible. Okay, think about what's happening here. The only way to get the middle terms to cancel is if one binomial has a positive and one has a negative, right? That's the only way to make the negative 10x and positive 10x, negative 10x. The only way they cancel is if they have opposite signs. Well, if those have opposite signs, right, then we have to have opposite signs here, which means in our last product, a positive times a negative will always produce a negative. So the only way for this to work is if this is a negative. So a sum of squares, what we have going on here, is prime. It's not going to be factorable ever. You can try, but if you multiply back out, it's not going to work. So this is called a sum of squares. A sum of squares is always prime. Okay, so that's why we could not go any further with the x squared plus 9 in that other problem. Alright, now the last one is similar. Okay, if you look at 50x squared plus 8, it's definitely not a difference of squares, but this one's not going to be prime because 50 and 8 have something in common. So 50 and 8 are both divisible by 2. If I factor out that GCF of 2, then I have a 25x squared plus 4 remaining. Now 25x squared plus 4 we've established in the previous problem is prime, but this entire problem is not going to be prime because to start we could at least take out a GCF. So even though 25x squared plus 4 is prime, we're not going to call this problem prime. We just can't continue to factor like we could earlier when we took out the GCF. So here it's not prime because we could take out at least a GCF of 2. So it's only prime. This would just be our final answer. Okay, final answer. You can't factor any further on that one. It's only prime if nothing is possible, if no factoring is possible. Okay, so those are our squares, and again, I'm hoping most of this looks familiar to you. Okay, how about cubes? The cubes we don't seem to be as comfortable with. They're going to work similarly, though. I could show you the multiply, but you can see I've got some formulas down here because these are a little more complicated. We can't use some tricks and patterns to try to cheat our way through, but we do have formulas, and using formulas tends to make things a little bit easier. So a sum or difference of cubes is going to be another polynomial with 2 terms. And doesn't matter this time if they're added or subtracted, but 2 terms. And what we want this time is any of our coefficients or constants to be perfect cubes. Okay, perfect cubes. And again, we're probably not as comfortable with these as we are with the squares. So let's just make a small list. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, this one's 729, and then 10 cubed maybe we know is 1,000. So these are our list of perfect cubes. We need any of our coefficients or constants to be perfect cubes, okay? And then we need our exponents on variables to follow a rule as well. Squares had to be divisible by 2 or even. These exponents have to be divisible by 3, which makes sense if we're dealing with cubes. So we want our exponents here to be divisible by 3. Okay, so let me show you some examples, and you probably see them here. These are examples of sums and differences of cubes. So there are 2 terms. We're looking at exponents that are divisible by 3, like 3 or 6 or 9. The plus or the minus doesn't matter. And then we need coefficients or constants like 64, 125, 8, 27. We need those numbers to be perfect cubes on that list that we just wrote. Okay, so if we've got that 2 terms, exponents that are divisible by 3, and coefficients and constants that are cubes, then what we can do is use one of these formulas to factor. Now notice the formulas say something cubed plus something cubed, or something cubed minus something cubed. So if it starts with a cube, no big deal, but the 125 isn't something cubed. So in the same way we rewrote the numbers in the squares problems as squares, we want to rewrite these numbers as cubed. As cubes, sorry. So I would make this problem x cubed minus, what are we cubing to get 125? Or what is the cube root of 125? It's 5. So I want to rewrite this so that it matches up with one of my formulas. Okay? So the first step is to rewrite the terms as cubes. And then every time we factor a sum or difference of cubes, again, we're going to use the formulas, but I actually don't have the formulas memorized myself. I just have memorized like a pattern, I guess, with the formulas, where we're always going to be factoring into this binomial and then a trinomial. So a binomial and a trinomial both times. So I like to set up my parentheses for my binomial and trinomial. Parentheses for binomial, trinomial. So I know that this is going to factor into a binomial and a trinomial, so I would set those parentheses up. And then if I look at the signs here, if it starts with a plus, this will start with a plus, and then it switches to the opposite. This one starts with a negative, this one starts with a negative, and then it goes to the opposite. And then the last sign is always positive. So the signs are, I remember this as soap, okay? Oops, I thought I had my highlighter on. My signs are the same, then the opposite, and then always positive, soap. So I have to fill in my signs, which are the same as the original, and then the opposite, and then always positive. Always positive. Okay, so the same sign, which is a minus, then the opposite sign, and this last one's always a positive. Okay, and then what's going to happen is the bases of the cubes go into the binomial. Right, so see how we have a cubed, b cubed here, and then just a and b here? So the base of the cube and the base of the cube, they go here. So in this case, it's the x and the 5. So I'm going to drop those bases into my binomial. Now in the formula, either formula says here, I take the first number that I have and I square it. So if I took x and I squared it, that would go here. In the middle, it says take the first and multiply by the second, the a times the b. That's what I have here. So a times b is going to give me a 5x. And then at the end here, b squared says take what I have here and square it. So take the 5 and square it to get 25, and now we're factored. Okay? So drop the bases into the cubes, and then we square the first term, multiply the two terms, and square the last term. Square, multiply, square. Okay, so let me show you now all at once. So number 10, what are we cubing to get 8? X cubed. Well, 2 and an x. And then what are we cubing to get 1 would be a 1. So this is going to factor into a binomial and a trinomial. Signs will be the same, so positive, and then the opposite, and then always positive. And then the bases of the cubes come down, so I'm going to drop down the 2x and the 1. And then here, I square my first term. So 2x times 2x is going to be 4x squared. In the middle, I multiply my two terms. So 2x times 1 is 2x. And then at the end, I multiply my second term. So, square my second term. So 1 times 1 is 1. And that's my completely factored answer. Okay? Not as nice, but definitely works. So let's try that again. What are we cubing to get 64? Would be 4. So 4x would make 64x cubed. 4x cubed would make 64x cubed. And y is already a cube. Cool. So now this is going to factor into a binomial and a trinomial. Signs will start the same, so minus there, minus there. This one's going to be the opposite. Last one's going to be positive. The bases of my cubes are going to drop down. Okay, so bring down the 4x and the y. So 4x here, y here. And then square 4x times 4x to make 16x squared. Multiply 4x times y to make 4xy. And then square the y to make y squared. And there it is. Alright, if you're feeling pretty comfortable here, and you want to give this a shot, then go ahead. If not, let's see, x is already written as a cube. We are cubing 3 to get 27. So binomial, trinomial, same sign, opposite sign, always positive. Bases come down, so x and 3. Square this guy, x squared, multiply the 2, 3x, and then square this guy, that makes 9. And there it is. Okay? And I feel like I'm flying through these. Hopefully you're keeping up. If not, pause it, rewind it, watch it again. Alright, here. What are we cubing to get x to the 6th? Remember we said these exponents had to be divisible by 3. So 6 divided by 3 means there had to be an x squared in there. And then 7 cubed is going to make the 343. So binomial, trinomial, same sign, opposite sign, always positive. The base of the cube, the bases of the cubes come down. So x squared here and 7 here. And then I'm going to square. So x squared times x squared is going to give me x to the 4th. Multiply. That's going to give me a 7x squared. And then square. That makes a 49. Alright, last one. Okay, what are we cubing here to get 729x to the 9th? So that's going to be a 9x to the 3rd power. 9 cubed would be 729, and x cubed would get me back to that x to the 9th. Okay, and then 2 cubed would get us to that 8. So binomial, trinomial, space here, trinomial. Okay, base, let's see, same sign, opposite sign, always positive. Drop those bases down. So 9x cubed and 2 square. What's 9x cubed times 9x cubed going to make? Well, that's going to give us 81x to the 6th. Okay. And then we're going to multiply 9x cubed times 2, which is 18x cubed. And then we're going to square. 2 squared makes 4. Alright. Now again, wasn't really checking on all these, but we can definitely check this. It's just a lot of work. But I'll go ahead and show you on this last one here. If I wanted to check to make sure that I did this correctly, then here, 9 times 81 is going to be 729, and we're going to have x to the 3 and 6 would make 9 altogether. Here, we would have 9 times negative 18, which would be a negative 162x to the 6th. And then here, 9x cubed times 4 is going to be a positive 36x to the 4th. Here, we're going to get a positive 162x to the 6th. Here, it's going to make a negative 36, this should have been a cube, sorry, x to the 3rd. And then at the end here, a positive 8. And what happens? Cancel, cancel, and we are left with the sum of cubes that we started with. Okay? So let me just get rid of this because it's really ugly. But you can definitely check your work, as mentioned, if you want to double check your factoring. Okay? And again, I think I kind of flew through that, but we're really just using formulas, and if the way I explain the formula is complicated and you want to just try to follow it out, then that's totally fine to do that. Let me just show you in the last one if you're more of a formula person and you don't like the process that I was trying to explain here. Okay, so I said, what did we have there? 729 x to the 9th plus 8. Well, we still want to rewrite these. This was 9x cubed being cubed, and this was 2 being cubed. Okay, now if you're more of a formula person, the formula for a sum of cubes says if we have something cubed plus something cubed, then it's going to factor into a plus b, and then a squared plus ab, and then, oops, this should have been a minus, sorry. Minus ab and then plus b squared. Okay, so if you're more of a formula person, in this particular problem, instead of a being cubed, we have 9x being cubed, and instead of b being cubed, we have 2 being cubed. right? So in place of a, we have 9x cubed. In place of b, we have 2. So here, we're going to plop in a, which is 9x cubed, and then we're going to plop in b, which is 2. And then here we have to take a and we have to square it. So a 9x cubed squared is going to give us 81x to the 6th. Minus, we got to multiply a times b, 18x to the 3rd. And then at the end here it says take b and square it, so 2 squared is going to make a positive 4. So I think it's pretty similar, but if you're just more comfortable laying it out with the formula, then absolutely use that method. Okay, and as always, if you're struggling, feel free to reach out for some additional help. Alright guys, take care.